Swayam Prabha. Digital India. Educated India.
Alright, so great. So we have pretty much all the stability notions that we require covered, yeah, pretty quick, yeah. Once you understand, like I said, stability, uniform stability, attractivity, you are more or less done. All the other notions are just, you know, sort of combinations of one or the other of the two, yeah, and you sort of understand how to strengthen them, yeah. You do not have to necessarily remember the sequence and all that. The first strengthening is imparting uniformity, which is independence with respect to initial time, and then the second strengthening is sort of giving some kind of a global property, which is basically removing bounds on initial conditions. Okay, so initial x0, if it's unbounded, that is, you can allow for any initial condition, then you have global properties. All right, simple, great. And this is very critical for nonlinear systems, of course. For linear systems, this is irrelevant. Global properties and local properties are all the same. Yeah, there is no difference between local and global for linear systems. Uniformity is obviously there. If you are talking about time varying linear systems, you still have to talk about uniformity. Okay. So again, the other thing to also remember is that if your system right hand side, that is f, yeah, we talk about systems of the form x dot equal to ftx, right. If this f here is independent of time, there is no time explicitly appearing on the right hand side, then the system is uniform for free. There is no uniformity to be considered separately. Okay. So these few things always remember: linear systems, local, global, no difference. If the system right hand side function, that is vector field, has no explicit time argument. Why do I keep saying explicit? Because the states themselves are functions of time when you solve them and all that, but if time is not explicitly appearing in these expressions, then the system is time invariant or autonomous, yeah. These words are used exchangeably for continuous systems, yeah. So then uniformity is free, you do not have to evaluate separately. If you obtain global asymptotic stability, you have obtained global uniform asymptotic stability. Okay, all right. Excellent. So just keep these in mind. Now we sort of go to these examples, right, these interesting examples that sort of give us different funny cases, if you may, yeah. So this is exactly the question that you asked, a system which is attractive but not stable, yeah, this is the system, yeah. Unfortunately you cannot solve this by hand at all, yeah, no analytical solution, but the phase plane plots look like this. Okay, so this is x1 dot, this is x2 dot, this is the system. I mean, you can think of it as some kind of a constructed system, I guess, alright, but well, it exists. So yeah, so the phase plane plot, like I said, is just a plot between the two states, in this case x1 on one axis and x2 on the other axis. So there is a sort of a bifurcation in this system, that is inside this blue sort of a aerofoil type shape, all the system trajectories look like this. Okay. So how do you make the phase plane plot? It is very standard in MATLAB, Python and so on. You basically give a bunch of initial conditions and you look at how those initial conditions evolve. So in this case, if you start an initial condition here, it will evolve along this like this. So you get an idea of what is a phase plane curve. So in fact, in MATLAB you have standard functions which will directly make phase plane by automatically randomly initializing, and then they will just directly make the phase plane plot for you for several cases. So the basic idea is this system is such that any initial condition inside this sort of bifurcation will have this kind of a shape. Okay, they will all look like this, and if your initial conditions are outside, then the trajectories look like this. Okay, so if you start outside, trajectories look like this. Okay. So, the interesting thing to see is it's attractive, right, because it's wherever you start, you are always getting to the origin, right. If you start inside, outside, it does not matter, it's going to just do this and go, or it's going to do this and go, it does not matter, it's going to the origin wherever you start. Okay. So, attractive, in fact, you can even claim global attractivity in this case. Yeah, I do not know about uniform, well, I guess it is uniform for free, no time argument on the right hand side, right. So, it is uniform, in fact, it is globally uniformly attractive and probably the best attractivity property you can imagine, right, but it is not stable. Why? Absolutely. Look at this, if you give me any epsilon ball, okay, any epsilon ball around the equilibrium, origin in this case, right, you make an epsilon ball like this, I have actually made the ball very specifically for that, you make the epsilon ball, yeah, then you cannot remain in this epsilon ball for any delta ball. Why? Because any delta ball will definitely have initial conditions outside this guy, right. If your initial conditions, well, actually it does not even matter, it is outside, actually it does not matter if it is outside or inside, yeah, there is no initial condition which will remain inside the epsilon ball, okay, they will always go out like this, yeah, if epsilon is like this. Now, if I, of course, if I make a very large epsilon, let us see that case also. Alright, great, I made this epsilon ball now, okay. Now what, does this work? Definitely, okay, unclear if this works or not, but there is a hope that it might work, because if I take, I mean, but potentially I could take really small delta like this, so that the trajectory that's, see the inside trajectories are not a problem, this sector trajectory is not a problem, because they will remain inside this wing and I deliberately made epsilon larger, right, but any trajectory starting here has to go around this. Now, I do not know if it will remain inside this or not, but the point is if I make this delta really tiny, I am sure it is going to hug this very closely and then not escape this circle, okay. So, there is a possibility of finding a delta, but that is not the stability question, right. The stability challenge is that you give me any epsilon and I can give you a delta, yeah. So, for large epsilon, yeah, seems like great working, but for small epsilon, no, okay. So, then it's, that is it, I do not have to do anything further. If it does not work for even one particular choice of epsilon that you give me, system is not stable, okay. So, system is not stable, but it is attractive, okay, alright. Then there are these simple nice examples like this pendulum, yeah, the nonlinear pendulum, the actual pendulum, it has a equation that looks like this, right, and I do not have to actually do anything to prove that this is asymptotically stable, you can just, I mean I can prove it not by solving it, difficult to solve this system also, just because of this sinusoid you will not be able to analytically solve it, yeah, but you can just look at the movement of a pendulum, you know that it is attractive, yeah, because of this damping term. This damping will come usually from the friction in the pivot point. So, if you make any pendulum move, it is going to stop at the bottom, right. So, it is attractive, yeah, the bottom position, that is theta equal to 0, is an attractive equilibrium, right, and stability is actually rather easy in this case, yeah, in the sense that I can guess it, yeah, but again I cannot analytically solve it, yeah, although this system looks so simple, still I will not be able to analytically solve it to get stability. How I would get stability is by linearizing, yeah, I would linearize this will become x2 dot is minus x1 minus k x2 around x1 close to x1 equal to 0, near x1 equal to 0, this becomes x1 dot is x2, x2 dot is minus x1 minus k x2, okay. So, that is actually near x1 equal to 0, if I linearize I will get x1 dot is x2 in and well x1 equal to 0 and x2 equal to 0, and x2 dot is minus x1 minus kx2, and of course k is positive. So, this is a stable system, right. This is in fact a asymptotically stable system, but it is definitely stable. Okay. So, this is one of the methods that I do not discuss in this course, but it is possible to get or obtain local properties of a nonlinear system by linearizing the nonlinear system and obtaining the linear system and looking at its corresponding stability. So, if you linearize a nonlinear system and the linearization is stable, then the nonlinear system is locally stable. Linearization is asymptotically stable, nonlinear system is locally asymptotically stable. Yeah. Why I do not discuss this particular method is because this method does not tell you how local is local. It just tells you that if the linearization is asymptotically stable, nonlinear system is locally asymptotically stable. It does not tell you how local, it does not tell you the delta in those definitions. Okay, and a lot of times you need to know those. Okay, I mean, if you are especially wanting to operate such systems, you actually want the value of that, the basin of attraction that it is called. Yeah. So, Khalil uses this word a lot, basin of attraction. Basically, it is the delta in the attractivity definition. Okay. So, we need to know that in a lot of cases, which is why I do not talk about that method here, but anyway, for this particular illustration it is okay. So, this is an asymptotically stable system, yeah, local, yeah, not global. Okay, not global because the inverted, there is an inverted position, that is x1 equal to pi, which is also an equilibrium. 0 0 is an equilibrium, pi 0 is also an equilibrium, right, for this system. Okay. So, the pi 0 equilibrium is unstable. Okay. We are not talking about, but so if you are talking about stability of this equilibrium, it is only local because there is another equilibrium. Okay. So, whenever a system has multiple equilibria, you cannot claim global properties. Okay. It is just like optimization, right. So, well, in optimization you still can, right, because you say if you have multiple minima, you just find the least minima in the entire domain and you say that is the global optimizer, right. Here you do not have any such thing. Here if you have multiple equilibria, then you can't say that any of them is global, because an equilibria itself means that you never move from there. So, this inverted position, if you start here and there is no disturbance, and obviously idealized system, if you start here and there is no disturbance, then this is a trajectory which does not converge to the 0 0 point. Yeah, there is actually a trajectory, right, because pi comma 0 is an equilibrium. So, if I start at this pi comma 0, I remain at pi comma 0, because the right hand side becomes 0, right. So, I do not move from there. So, this is a trajectory for all time, I remain here. Yeah. So, my property cannot be global, right, because if I start right here, I do not converge here, and global requires that for every initial condition I should be able to reach the equilibrium, right. In this case that is not happening. So, whenever you have multiple equilibria, it is virtually impossible to say that it is a, whatever you have achieved is a global property. Okay. Alright, makes sense. So, what most people do is they try to say that okay, there are some you have this equilibria, but it is an unstable equilibria, therefore in reality you will never actually stay here, and so on, okay, which is true, right. I mean, if you take a pendulum, even if you start here, you will never stay here, right. I mean, however much your damping is, even if it is slightly off from this, which it will be in the real world, you will go back to the 0 0 equilibrium, okay, but it is not global, okay, sadly, okay. So, remember that, not global property. Alright, this system is globally asymptotically stable for sigma positive, very easy, just solve it. Yeah, this is easy to solve. This is what you have, you get this is the solution. Yeah, believe me, this is the solution. Yeah, I checked. Okay. So, this you can see that as t goes to infinity, what happens? This term is going to go to infinity. So, this entire thing is going to go to 0. So, attractivity is guaranteed. I have to prove stability, but yeah, I mean, yeah, it is stable. I guess I have asked that as an example. Oh, okay, yeah, nice. That is an exercise to prove stability. Yeah, because attractivity is obvious, right? I mean, you do not have to do any work at all. Yeah, but stability you might have to do a little bit of work. Okay. Okay. So, that is an exercise here. You have to prove that this is globally asymptotically stable. Again, I say only globally asymptotically stable because uniformity is free. Right hand side is independent of time. Okay. So, no need to evaluate uniform. If I say GAS, it is GUAS. Alright. Okay. Good. So, this is of course, I sort of wanted to give an example of non-uniform asymptotic stability also. Alright. So, you can have such examples also. So, all I do is I sort of introduce a function of time here. Yeah. If this was 1, just think about it, this is just a linear damped oscillator, right. So, spring mass damper if this was 1. So, but all I did was I introduced some time varying quantity here, and it so happens that the solutions look like this. I mean, so I mean it turns out that it is non-uniform asymptotic stable. Okay. So, basically you do not have uniformity in this case. In a lot of these cases it is not very easy, as you can see, to solve them and so on. If you look at this is just a linear system, by the way, yeah, linear time varying system. So, as soon as you go from a linear time invariant system to a linear time varying system, your life becomes pretty complicated already. Yeah, you do not even have to go to nonlinear. I mean, what I would say is linear time varying systems are sometimes harder to analyze than nonlinear systems, nonlinear autonomous systems. Okay. So, does not make your life significantly simpler or anything. Yeah. So, even to evaluate non-uniformity using these definitions would be rather difficult. Okay. Any questions? If you have a single unique equilibrium point for a nonlinear system, your question is, does asymptotic stability guarantee global asymptotic stability? I would say no. No, does not. You can have a case where you do not converge to that equilibrium also. Far away from the origin, you do not get to the origin. Yeah, I do not think this can be said in general, that if you have asymptotic stability, you have global asymptotic stability for a nonlinear system, just because you have one equilibrium. Okay. If you ask me for such an example, I will struggle a little bit. Yeah, I will have to think. Okay, I will have to think. I think a version of this Van der Pol oscillator might be such an example. Yeah, I have to sort of think about it. Yeah, there may be a version of a Van der Pol oscillator which sort of does exactly what I am saying, that it does not do, it's almost like this. In fact, if you look at this system, yeah, well, this is still nice, inside and outside in both places it is converging to the origin, but you might have some kind of bifurcation which beyond which it does not converge to the origin, but inside it does. Yeah. So, nonlinear systems can exhibit a very wide variety of behavior. So, I cannot claim that in general, if you say asymptotic stability, then essentially we are saying asymptotic stability implies global asymptotic stability, more or less, right? No, I would not have any reason to make a separate definition. No, escape velocity is slightly different because I see. You are talking about escape velocity in terms of launches, like in terms of launching and stuff. Yeah, I understand what you're saying. Maybe, yeah, maybe that kind of a model, yes. If you think of a rocket that you are trying to write equations for, and then you have gravity acting on it, so there is an escape velocity. If it's, so basically if one of the states is too large, then you don't come back and fall into the ground, but if your velocity is smaller than this particular number, so one of the states is small, then you do come back. Yeah, maybe if I model it appropriately, it will probably exhibit this behavior. So the model, I mean, I'm wondering, the model also has to exhibit this behavior. Physically, yes, absolutely. Yeah, physically, yes. So yeah, I mean, you can always, I mean, if you can think of it, then you can model it. So I guess you can have such an example also. Yeah. So nonlinear systems, very wide variety of behaviors. You cannot say that in general. Okay. All right. Any other questions? Okay. Good. This is one of the simplest examples, of course. Right. This is the global exponential stability. This is a linear system. Right. Like I said, linear system, linear time invariant system, especially, it's like exponential stability is any stability is exponential stability. Okay, nothing less than that. Speed, whatever, very fast. But again, linear time varying systems, that may not be the case. So it's a very fragile sort of a thing which works only for linear systems and not more. Alright. So like I said, for linear systems in general, uniform asymptotic stability and exponential stability are also the same, yeah. So there is no difference really. In fact, how do you evaluate it? You just look at the matrix eigenvalues and so on and so forth. Yeah, I mean, it's pretty simple, all of you understand how to do it. You can also do the Lyapunov tests and all this usual things that we have been doing, but you don't have to, but we will look at those conditions. Yeah. In order to look at those conditions, we have sort of redefined these matrix norm notions, but I am not going to repeat them. I believe you already know them. Yeah, just the notion of the induced norm repeated here. Then how to evaluate some induced norms, again repeated here, just the formulae. And then these inequalities, which are just the induced norm inequality, right. This inequality is coming from the induced norm definition itself, right, because induced norm is the supremum. Yeah, therefore norm Ax divided by norm x is always greater than norm A, okay, because it is the supremum, right. So for all values of x, norm Ax divided by norm x has to be greater than equal to norm of A. I hope that is evident, right, because sup is basically an extension of the maximum, right, and that is how you get this. Okay, did I say this correctly? I said it the other way around. Sorry. From here you have norm of A is always greater than equal to norm Ax divided by norm x. Yeah, just by virtue of the fact that I took a supremum here. Yeah, from here I get this. Sorry, I said it the other way around. Yeah, so it's just the norm inequality, induced norm inequality, and this is the Cauchy-Schwarz like inequality, like that we sort of proved for general vector spaces last time. Okay, so when do we say that? Okay, this is a little bit of proof. So anyway, that's fine. So one of the conditions for stability is this guy for linear system. So this is a general time varying linear system. Okay, with some initial condition, because I have time dependence, so therefore my initial condition is also at a particular initial time, not necessarily 0. Alright. So the condition for stability is something like this. Okay, basically what is this notation? I hope all of you know this notation. This phi, capital phi by the way, is the state transition matrix, yeah, or the fundamental matrix, whatever you want to say, yeah, and you also know that the solution at any time can be written as in this way, yeah. This is how you use the state transition matrix. In fact, the state transition matrix describes the flow for the linear system, yeah, because it tells you how you map the, if you fix the t, it tells you how you map initial conditions, right, different initial conditions. I can take different initial conditions and I keep multiplying with phi, I get a flow, yeah, how my initial conditions are getting mapped, okay. So, this is just a linear equivalent of whatever the flow. In fact, that is why you see the similar notation getting used. There it was a small phi, here it is a capital phi, yeah. So, what we say is the condition for stability is that the norm of this matrix is bounded by some function of initial time, okay.